Greetings. A warm welcome to my poster presentation. This is Dharineesh, an undergraduate student in BTech Bioinformatics from Shastra Dharineesh University, India. The Transglutaminase 2, that is TG2, is a calcium-dependent enzyme mostly found in mammals. These enzymes catalyze the post-translation modification of glutamine residues on the surface of its protein. It contains four domains, namely N-terminal beta sandwich, the catalytic domain, and two C-terminal beta barrel domain. It has two conformation states, the open conformation and the closed conformation, as shown in figure 1. In open conformation, peptide, that is ligand, is bound to the active site, whereas in the closed conformation, GDP or ADP is bound to the active site. The superposition of both conformation is shown in figure 1c. Celiac disease is an autoimmune disorder caused by the ingestion of gluten. The gluten enters into a cell and binds to the TG2 enzyme. The TG2 enzyme gets activated and it causes deamination of gluten, which acts as a foreign particle. This gluten causes the activation of anti-transglutaminase antibodies and affects the small intestine. Our study workflow is shown in figure 2. We collected 9 human TG2-PDB structures from the RCSB PDB database. Among these 9 PDB structures, 5 are in closed conformation and 4 are in open conformation. We use Gromel's package to perform molecular dynamic simulation. Before performing molecular dynamic simulation, we modeled the protein structure in Swiss model server to fill up the missing residues. We constructed 4 setups to perform 200 nanosecond molecular dynamic simulation. They are open conformation with 2 calcium ion, open conformation without calcium ion, closed conformation with 2 calcium ion, and closed conformation without calcium ion. We used dynamics domain, that is DINDOM server, to analyze protein domain movement. We used PRODI for closed-grain modeling with crystal structures. We used elastic network model to build the closed-grain model. Here we used Gaussian network model GNM and anisotropy network model ANM. We collected non-synonymous NSSNP from the SNPDB database. We used 8 sequence-based and 6 structure-based prediction tools to analyze the effect of NSSNP in the protein structure. Initial and final snapshot of 200 nanosecond trajectory of both conformation are shown in figure 3. For the open conformation with calcium ion and open conformation without calcium ion, the RMSD difference were 2.3 angstrom and 2.5 angstrom. For the closed conformation with calcium ion and closed conformation without calcium ion, the RMSD difference were 1.4 angstrom and 2.2 angstrom. There is no significant domain movements in closed conformation without calcium ion. The result of DINDOM is shown in figure 4. The arrow represents the rotational vectors. The beta 2 domain showed the most mobile domain movements as compared to the other domains. The high rotational angle value observed in the open conformation without calcium ion. We calculated the solvent accessible surface area of the active site to check the local changes in the protein and is showed in figure 5. The higher SASA is observed in the open conformation without calcium ion compared to the open conformation with calcium ion. The closed conformation has no significant difference in SASA. Calculated the mean square fluctuation versus B-factor correlation to validate the JNM model is significant or not. The MSF versus B-factor plot is shown in figure 6. The directionality of the first three slowest modes are shown in figure 7. The dynamics around the active site residues are more subdued, implying that the fluctuations do not affect the ligand interaction. The global cross correlation map are obtained from the ANM model and is shown in figure 8. We observed that there are relatively more negative correlators than those that are positively correlated. The comparison of hotspot residues in the first five fastest modes are compared in figure 9. The presence of the active site and the hotspot residues are shown in figure 10 and 11. In open conformation, the hotspot residues are located near the active site. In closed conformation, the hotspot residues are far away from the active site region. For NSSNP analysis, we use multiple prediction tool for consensus ranking approach to classify the efforts on sequence and structures. For sequence-based predictions, 4 out of 8 predictions were SNP aperture structure. For structure-based predictions, 6 out of 6 predictions were SNP aperture protein. Using the cutoff, we identified and tabulated the 10 mutations for comparisons. We have taken the absolute solvent accessibility value from the DSSP output and we calculate the relative solvent accessibility and it's shown in table 1. Based on the table 1, we hypothesize that the NSSNP are highly likely to cause the drastic change in TG2 structure and its dynamics. In this study, we hypothesize that the open conformation without calcium shows large conformational change. This study provides foundation for the future investigation, both through computational and experimental approaches to gain a deeper understanding of the functions and structural dynamics of TG2. Thank you so much.